This video is going to go over the part of the internals between quotes of the GCC compiler. We're going to explore a little what happens when you issue the GCC command, and this is going to cast light into the various steps of a compilation process. Okay, pre-compilation, compilation, linking, and finally generating the executable that you are going to run. So let's get started. Well, the first observation I would like to do here is programming, and I'm not talking about software management or software engineering, but just the activity of programming, of coding, is actually an activity that goes through many steps. Okay, what you see on this slide is just a list of a couple of things that you need to do when you are coding a program. The first step, of course, is designing. So in this class, that means using flowchart, maybe using pseudocode, using a draft piece of paper to put your IDs together and to figure out what kind of algorithm you want to implement. Then the next step is editing. You get on the keyboard, you connect to our Linux system, you open an editor. No matter what this editor is, hopefully it has syntax coloring. You're going to code your code, you're going to see it take shape in the language of your choice. Then the next step is compiling. Once you have typed the code that you wanted to implement the design that you thought of, then there are going to be other tools that come to the rescue. Those tools are compilers or compiler suites. Okay, so in our case we use GCC. GCC is going to take the plain text that you typed with your editor and is going to attempt to generate machine language, an executable from it, a program that can run. So at this level you can have syntactical errors. Okay, so your compilation will fail, you'll have one or more errors. Always start by solving the first error, and then once it is solved, chances are that the next 50 errors that are after it were just the compiler not understanding what your program meant because of the first error. So the rule here is always correct the first error, then recompile, move on like that. Okay, other thing that can happen when you compile, you have warnings. So warnings do not prevent the compiler to generate an executable. Errors do. So if you have errors in your compilation process, the executable that is on disk, most likely this is the last executable that you compiled successfully. Okay, for example, a.out. It's not going to be replaced by a new version. Errors prevent compilation process from completing. Warnings let the compiler go to completion and generate an executable. However, the compiler, through a warning, is trying to tell you that something is suspicious in your code. Most of the time, understand by that 99% of the time, a warning needs to be resolved. A warning is something that is actually important, a potential bug. In some cases, the warning is just something that can be overlooked. For example, warning, the last line of your file is not a blank line, which GCC loves to complain about. Well, this is not going to cause your executable to misbehave. Every other warning, I would say in this class at least, should be seriously investigated. So we are at step 3 here. Designing, well, the only thing that can help you do that is your brain. Editing, you have a couple of tools here that help you visualize the code a little bit more colorfully and practically. Then you have the compiler that is going to help you check for syntactical error, check for warning, and if all of those work, generate an executable. This is not the end of the story. You can write code that is perfectly syntactically correct in any language, compile it, generate an executable, and yet have errors, runtime errors, errors that are going to be more of a logical type. For example, instead of dividing x by y, you divided y by x. Well, the compiler has no idea about that, has no way to detect this as being an error. It's going to compile, generate an executable, and when you run it, you're going to notice that you don't get the result that you were expecting. So by any mean, once your code compiles, this is not the end of the story, you still have to look for runtime error. Code checking can be a way to do this. As a matter of fact, code checking, and there are different tools out there that exist. Lint is one of them, Smash is another one. Code checking is a step in programming that allows you to apply to your code a couple of tools which are going to look for well-known pattern of errors. And these tools are going to point out to you, well, in this particular section of your code, you are doing this and so, and this might be a problem. Please double check. The intelligence of the system here is fairly limited, okay? The computer doesn't understand what your program is supposed to do, so there is very little that can be done here to anticipate very subtle error. But you can still have tools like Smash, for example, that are going to look in your code for pattern of well-known traditional errors that generation and generation of programmers have done and point them out to you. The next step, testing, debugging. We already talked about that during our first week of course. The purpose of testing is to pretty much put your program to the test, make sure that your program, given a given set of input, is going to produce output that were required for your program to produce according to the problem's specification. So if I give you an assignment that say you need to have a program read only strictly positive integers, if I start inputting to your program negative number, your program should catch that issue and display an error message and invite me again to enter some data. As you develop tests, as you put your program through a test harness, you are going to have misbehaviors happening. Your program is not going to do what it's supposed to do, and this is where you are going to enter debugging. So realizing that a given test fail is not the end of the story ever. Your test fail, you don't jump to your code and start changing things randomly almost without even knowing why you change them, just so that you can shake your program, literally speaking, until it behaves properly. No. When a test fails, you go back to your code and first thing you try to understand why your code is producing this unexpected behavior. Once you understand why, you will understand what part of the code is not doing the job you expected it to do. And then you can start thinking about how do I modify it so that it behaves as expected. So never lose of sight the need for intentionality. Every time you modify something in your program while you test and debug, it has to be because you have an intent. It has to be because you have an idea in mind. If I change this, this is going to do that. This is going to fix this problem and give me the behavior I expect. Never go with random changes just for the heck of it. The next step, purifying. Once again, different tools. I just give you names here for your culture, but the code purification step is actually a way to compile your program, generate an executable, and introduce in that executable some instrumentation, some extraneous code, which is going to just check things during execution. So this used to be really used in C++ development with a tool called Purify from Rational, which allowed you, for example, to check that while you were iterating in your program, you were not getting out of the boundaries of your arrays and things like that. So everything that can be checked at runtime is generally checked by a purifier. Problem with that kind of tool, well, all those little tests that are added automatically to your code to make sure that your code doesn't introduce well-known bugs, all those tests are going to run at the same time than your code. So instead of going at the regular speed you could expect from your hardware, you are going to have a program that executes much slower because it is constantly verifying and searching for a wide array of potential problems. So this is something that you do just to test your program. You compile it with one of those purification suites, and then you run it one time or several times, depending on the nature of your program. You collect a report that tells you, well, in this and this area of the program, you might have this and this potential problem, and you go back to testing, debugging some more to assess the gravity of those problems. Profiling and optimizing, the next step. Well, profiling and optimizing means that once you have a program that works fully, which you should by this line I'm drawing here, once you don't have any more bugs, you might want to look into, well, am I going as fast as I could? So that can entail some design issue, that can entail some implementation issue. You can optimize a little at both level, and you can then use profiling to just make sure that all the parts of your program are executing. When you are designing a series of tests, when you are designing a test harness for your program, you always take care of having many different tests. So that what? Well, so that if your program has an if statement in the middle and 2 branches, then you are going to test the code in both branches. So you need to provide input to data that is going to trigger both of the branch of the if. Well, try to think more generally to this idea here. What if we have some code that is 5,000 lines long? We have 100 function or method inside of it. We would like to make sure that when we run our test, all the methods have been run at least once, so that we have a chance to at least, detect a problem in each of them. So this is what profiling is all about. And generally this used to go only as the optimizing step. Now more and more people are making sure that when they develop test on us, when they are testing their program, they are testing every possible execution path in their program. So profiling over the years pretty much got merged into testing. And then once you have your application, well, you'll need to deliver it to your customer. You'll need probably to package it. So Debian, Red Hat Package Manager are things that are really common in Linux environment. You are going to prepare your application for deployment. You are going to prepare it to be installable on any system. So this was a rather lengthy overview, but this is something to get you to think differently about programming. Okay, it's not just about rushing on the keyboard. For your information, in this class we are going to pretty much focus on this part: design, edit, of course, compiling, and then we are going to also develop a little your skills as far as testing and debugging goes. The other tools are tools that you are going to encounter if you like to go into programming as a career. Okay, back to GCC and a lower level of concepts here. Let's try to figure out what GCC does for us. Okay, we know that GCC takes care of the compilation step, but actually GCC does many different things which are all grouped under compilation steps. Everything from pre-compilation to actually generating the executable. So for the sake of this slideshow, we are going to use this little program here. Pan include stdio.h, int main, printf hide. This is pretty much hello world. We store it in a file named helloworld.c. And this is here the command line that you would use to compile it. You could use gcc and just helloworld.c. If you use gcc and just the name of the C file, what it does is generate an executable named a.out. Okay, you have seen that already in the videos. You have practiced it on the server. Now, you have an option here to specify -o space and the name of an executable. And what it's going to do, it's going to instruct GCC to compile this file and generate this executable, HW. Unlike Windows system, Linux system do not require you to have a .exe extension after your executable file. You can name them with that convention if you feel more comfortable with it. It's not necessarily a bad idea, but on a Linux system, it's not mandatory. If you try to execute a file named HW, if it has been compiled and it's an executable file, it will just execute without the need for the .exe suffix. So this is the overview. Okay, this is what you do to generate the code for all of your exercises. Now let's move on and open the box. Let's see what happened when you issue this GCC command. First step, this slide here is going to illustrate that when you generate your executable HW here in this example, you can then take a look at it and get some information about what HW represent. I already told you that the .exe suffix was not necessary. Well, let's take an example here. I compiled hw.c into the executable HW. I'm using command line here, but you can use your graphical user interface to get some information about that file. You see that it tells me here the size of the file, who is owning the file, and you can see here some access right. RWX stands for read, write, execute. This line is telling me, and you can see it also for your GUI by just putting your mouse over a file or right-clicking and asking for property. This shortcut here tells me that RWX, the first 3 letters tell me that the owner of the file, and this is a username for the owner of the file, can read, write, and execute it. So this is here that I see that this file can be executed. Then people, other users that are in the same group, can read the file. They cannot write it. You will notice a dash instead of the W, and can execute it. And finally, other people that are not in the same group, can just read and execute that file, r-x. So this is a way a Linux Unix system is keeping track of the permission on a file. Permission for the owner, the people in the same group, like students, for example, and then other people that are not in the same group than the owner and that are not the owner. Well, so this is the first way that you can see that a file is executable. A second way you can see it is by going into your console, typing the command file space and then the name of a file, for example HW in our case, and this command file is going to tell you what this file is all about. What is it? This is an ELF 32-bit executable compiled for an Intel x86 CPU. So if you are in doubt that a file is executable, this kind of command here or this kind of command here on the Linux system will tell you exactly what the file is about. If you are curious about how exactly executable files are recognized, I suggest you look at the file USR share magic. This is not a joke, actually. This is the name of the file, and it contains actually an indication that helps the operating system recognize which files are executable and not. If you have questions about that, email me directly, since this is out of the scope of this course. Okay, now we are still at the high-level view somewhat. Now let's try to break down things into steps. Okay, we can, if we want, issue command lines that are going to compile our programs in multiple steps. For example, this command line here, GCC -c, dash always precedes an option. Okay, so -o means output, produce that executable. -c mean you are going to compile simply the object file. You are not going to compile the full executable. A little remark real quick here. When I talk about object file, this has nothing to do with object-oriented programming. Okay, I'm going to try to explain that in the couple of upcoming minutes, but just up front, this has nothing to do with Java, this has nothing to do with object-oriented programming. So this first command line here is going to take our source file, and it's going to generate a file which has the same name, but the .o for object file suffix. This file, you can obtain information about it by using the two commands that we discussed in the previous slide. Okay, ls to see if it's executable or not, and file to see exactly what it is. And this one is not an executable. You cannot run it. Then we can issue a second command, which is going to tell GCC generate an executable named HW. That's what the option -o HW space HW does. And we are going to say generate this executable from the object file. So this command takes the object file that we built on the previous step, generates the executable. Well, beside illustrating the fact that an object file is just an intermediary step toward creating an executable, this also shows you that you can instruct GCC to do things step by step. By default, GCC is doing everything in one big swoop. Okay, generate the object file, then take it, generate the executable file, and you don't see even what's happening. We are starting to decompose things step by step so that I can introduce a couple of the compilation related concepts you need to learn in this class. So let's move on to the next slide. This is a real story. The real story is a little bit even more complicated. You start with a source file, and when you call GCC, GCC does everything which is in this big blue box. That is, first step, call a program called generally CPP0, which is a preprocessor, which is going to take your source file, and it's going to handle every pre-compilation directive, every line which starts by a dash symbol. For example, #include, -include, #define, etc. Whatever starts with a dash or pound symbol is going to be actually handled by the preprocessor. This results in a file named the expanded source file, which has the same base name as your file, but an extension .i. Once this is done, this file is going to be handled by another program. So GCC really is a sort of script which is calling 4 different programs, one after the other. The second program, CCL, is a compiler. It's going to take your expanded source file, which is still written in human readable format, and generate an assembler file, same base name .s extension. This assembler file is going to be fed then to a compiler, to an assembler, sorry, which is going to generate the object file from it. The subject file is going to be fed then to the linker, which is going to take this almost ready executable here, and it's going to merge it, to collate it with other .o files that you might have written, with library files, .a generally, and it's going to put all of this together to form your executable. So this is really a 4-step process. If you want to have more information about GCC, I suggest that you look on the web or you issue on your console as a command man GCC. That's going to give you probably more detail that you want. The only thing I would like to point out for now is that there are different options that you can use to tell GCC to do all the work up to a certain stage. So if you want to do just generating the object file, you're going to use a specific option. You can tell GCC to stop after generating the assembly language file, or to stop after generating the expanded source file. So we're going to use those options to explore each step one by one. Let's start by the pre-compilation step. This is our source code. Okay. The first thing that GCC will do is call the program CPP, to use a C pre-compiler pretty much. You could obtain the same effect by using this command line here. What this program is going to do, this program is going to take care of all the lines that start with a pound symbol. For example, in our little program there's only one here, pound include, and the pre-compiler is going to identify which file you want to include here. Find it somewhere on the file system. For example, all the standard C library files are located in /usr/include. So stdio.h will be just right there, /usr/include/stdio.h. The pre-compiler is going to take the content of that file and it's going to just replace that line here, which I'm crossing out right now. It's going to replace in your code that line by the full content of the file stdio.h. So it's really doing pretty much a cut and paste for you. Okay, it replaces pound include smaller than stdio.h greater than by anything that is in that .h file. And this now, all of this constitute your expanded source file. So this is really a basic step. Okay, pre-compilation is really something relatively easy to do. Once we are there, we are going to take this expanded source file and we are going to apply a step which is going to translate what is written in a high-level programming language into a lower-level programming language, something that is closer to the hardware, closer to the CPU particularities. You can see on this slide that we take everything we wrote here and we translate it in assembly language. Those of you who already took computer organization are already familiar with assembly language. If not, don't worry, you are going to get there in time. But the bottom line is that you can see already here from 40,000 miles that here we have something that is really human readable. It's a high-level programming language. Here this is a much lower-level programming language. Okay, so this is the first thing that happens to really transform your program into an executable. But this here is not yet an executable. This is still something that a human can open with a text editor and read. Of course, the language is a little bit more harsh and difficult to read, okay, but it's still human readable. Next step. Next step, we are going to take this translation of our code into an assembly assembly language file, and we are going to feed it to a program called an assembler. And the role of the assembler is really to take this assembly program and translate it into machine code. Machine code is just binary, 0 and 1s, okay? Machine code is specific to a given architecture, a given platform, for example, Linux on Intel i386 CPUs, and machine code is going to be pretty much human unreadable. I guess you could make the effort to try to read it, but it's just a bunch of 0 and 1. Somebody really is going to be able to do that. So, at this point, we make the translation from a human readable format, even for a lower level one than our high level programming language, into something that is really formatted for a specific machine. Once we are there, next step, we take this object file, we take over object file that are part of our application, we take, I'm simplifying here, but over object file that are standard C library, that contains the standard C library implementation of printf and scanf and so on and so forth, and we are going to feed them all to the linker. LD is the name of the linker program on our system. LD is going to take all of those pieces of compiled code and put them together so that when we call printf, the code for printf is already pre-compiled somewhere in a library file. When we call printf, the role of the linker is going to connect the call as it appears in our program to the code that is in one of those libraries that are already compiled and available on the system. And what results out of that is a single file, which is our executable file. The slide here is optional. It just shows you that you can use GCC-V for verbose to force GCC to give you instruction on the screen about what it is doing right now. And if you do so, you will find in the middle of the text that's scrolling on your screen, you will find something that looks like this. I just spaced out the different options so that they are more readable. But this gives you a good idea that at the end of your compilation process, really what GCC does is calling the program LD. It's going to tell that program what kind of executable we need. In this case, the name of the executable format is ELF, which is specific to Linux and Unix system, i386, meant to run on an Intel CPU. You are going to have a couple of options that I'm not going to explain in detail now. Here, the executable name will be HW, and you can see here this path will change depending on your system, but you can see here that there are a couple of files that are specified. C runtime environment.o, C runtime begin.o, CRTN, CRTN, etc. All of these are pieces of code that are already compiled that are going to be appended respectively at the beginning and end of your executable to allow your executable to set itself up properly in memory when it started and to pretty much shut down nicely when your program terminates. So even if you write a piece of code which is completely empty, you will have already pre-made compiled code that is going to be appended to your apparently empty program to do something. And all of this is part of the C runtime environment. Okay, I think we are pretty much done with this first slideshow. So keep in mind a couple of things. The compilation process is multiple step. You can elect to instruct GCC to go up to a certain step. We're not going to use that a lot in this course, but this week, if you want to experiment with that, this is the way you need to do it. So the compilation process is multiple steps. Second main important point, what is a linker? What is a linking process? Well, from what we saw, the linker is pretty much the program part of this compilation step, which is going to put together your compiled code with other fragment of compiled code that belongs to the library, standard C library, or belong to other programmers that are giving them to you. Okay, so multiple step, importance of the linker, and pretty much these are the main two things that you have to take out of this presentation.